I'd like you to say hello to my little motor, the Mecapion, the SF50A motor. And this thing should be able to do 60 amps with no problem. I'm going to drive it today with the Argus. This is my little drive Argus. Copley's made this to run for vehicles, normally battery-powered systems up to like 48 volts. But there's also a 90-volt version coming out soon, too. You notice the connector on the development kit is very much beefier. This is like a 10-gauge wire here. So I've got to use an unregulated power supply or a battery system just to provide enough volts and amps for this thing. The motor power wires, they're rather large, and they did fit into the connector, which is really good. I have feedback from the motor. This is incremental encoder with Halls, but this is a plus drive, so it also takes like the BIS-C and other absolute encoders. And this motor should have an option for a BIS-C. I got this from the guys at Servo a while back. They've been using this motor in applications, so it's a good motor. The development kit has a stow on it, so I'm using my stow adapter here so that I can bypass the stow. That allows me to enable the drive. So with the stow installed, I can enable the drive. I'm using my RS-232 adapter to connect over the serial port. This is a can open version. First, the EtherCAT's coming out. This will be in a rugged format too for rugged applications, the standard 810F type application. And there's lots of jumpers and address switches for checking out the system. You'd probably want to lay out your own board. And the FETs are mounted on the opposite side of this Berquist-like material. So this is the heat spreader. This would normally be mounted to the frame of your equipment to pull the heat out. At 30 amps continuous 60 peak, it's going to generate a little bit of heat, but not very much. It's a Copley. So I got this APM series data, the Mecapion data, from Luca Nicolai of Servotecnica in Italy. And here's the motor. It's an 8-pole motor. Inductance, resistance, back EMF, inertia. This is some of the data we need to get this thing set up. The nice thing about this is they had provided at one time a sufficient amount of data so that on our web page we could include the data, motor data files. So here's the Mecapion files, and you can download these files. This is the incremental encoder with Halls, but it's a good way to get started. Just load the file, and it's got the encoder resolution and everything in it. We'll take a look at that. And then if you get the cable, you'll have to figure out how to wire it. The encoder cable has incremental encoder A, A0, B, B0, X, X0, or index, index0. And there's U, V, W, differential. We don't need differential. Single-ended is fine. So just hook up the U, the V, and the W, and don't do anything with the knots. There's a +5 in ground and a shield. Make sure the shield is connected to the frame, earth. Make sure this power supply has a connection to earth close to the drive. Keep the distance as short as possible. This heat plate can also be connected to earth when it's mounted to the frame. This Argus is new. This is the can open, GPM, P for can open. There's an E for EtherCAT. This data sheet doesn't show the 90-volt version. This is the 55-volt. This is the first one we've come out with. It's for vehicle applications, running on battery supplies, usually. 30 amps continuous 60 peak. There's a resolver version. We're going to do an 090. That'll get for higher voltages, higher powered systems. There may even be a connectorized version of this called the brick, which will maybe have higher voltages too. But you can see it's a plus drive. Some unique features about this is 422 option. That's standard, pretty popular in the rugged industry. You got your sine, cosines, and your incremental encoders and all the absolutes, plus resolver. You get some I/O, and it's a small package size, 3.1 inch by 2.4 by 0.9 inch. You know, this is 60 amps for 1 second, 30 amps continuous from the connector with the pins. You could probably do a lot longer for peak current. I don't need it in this application. We're just going to spin this motor fast. But if you needed 60 amps for 2 seconds, I'm sure we could give it to you. You just probably have to solder the module pins into the board so that the pins can handle all the current. There is a heatsink option. I'm not a big fan of a heatsink option. Haha, fan. Rugged applications don't like to use fans. I don't like to use heat sinks. I just mount this heat plate right to the frame of the machine and I have an infinite heat sink. So the FETs are on the opposite side of this heat plate. That's a heat spreader. That'll pull the heat right out. You can use a heat sink and a fan if you want. That's fine. But I like the frame, and the frame's a good way to get rid of the heat. The development board, again, it's got jumpers on it for inputs and outputs and feedback devices. So if you're using absolute encoders, you'll see the wiring diagrams for that. Just make sure the jumpers are taken care of here for the specific case. So I'm going to use CME2 version 7.1 beta 36, which can talk to the Argus GPM or GEM. And we'll take a quick peek at the basic setup here. It's a brushless rotary motor, incremental encoder with Halls. I got it in a CAN mode, buffered output, that's fine. So there is like a multi-mode capability with this module. That's very interesting because that lends itself to pulse and direction input, buffered output, or even emulated output. So I downloaded the Mecapion data, opened up the file, got some feedback. Let's do encoder loss detection. Calculate for initial tuning values. Yeah, the inductance is a little higher than the resistance. That's fine. So you can see 25 amps continuous 60 peak. Good initial calculated values. So we can double check the phasing. Just going to do a little manual phasing. You can see the as you go forward, the counts go up, counts going up. So this could be the forward direction that it's rotating. You can see the red indicator slightly leads the current vector in both directions. I got a Hall offset here of 150, so there's a wicked lead and a wicked lag. So I used minus 150 for the Hall offset. That's just aligning the encoder and the Halls for the commutation. So that's good. We got some current loop bandwidth here. These are calculated values based on the data given. Maybe the inductance is a little bit more than the 0.9. 600 hertz of bandwidth, that's okay for slow speed. If we want to go faster, well, we'll need more voltage for this motor. Today I'm running on 48 volts, but the 8-pole motor, 4 electrical cycles per second, we need to rotate the current vector fast enough. So we'll take a quick look at the tuning. We'll do auto setup checkbox current loop tuning. So we can give it some more gain, proportional. If it's a little too high, again, you get some overshoot. Back it down a little bit. No overshoot. Shoot for the integral. There's a little bit too much. There's a little wind up here. You can see the drag drop, a little overshoot there. Set it to 100. That should give us about a kilohertz of current loop bandwidth. I'm going to do the velocity auto setup checkbox. I'm going to take a look at the current, actual current. And don't go too crazy with the XL and decel. So this will give us a little more reasonable XL and decel. Still bangs back and forth here. It's a rockin'. So we can take a look at the, yeah, hitting 30 amps already for acceleration. The command and actual look pretty good. We can mess with the gains again, crank up the P till you get overshoot, then the integral. I'm gonna leave this alone because it looks pretty solid. Skip right to making a auto setup checkbox. Make a little move. I got some extreme acceleration here. I'm gonna go a little bit slower. And I'm going to add the current, actual current. I'm going to add the, let's do a single rev from here. We'll let the control panel open here. Okay, I got like 30 seconds to make this move, so here it goes. So you heard the bang bang. That's the acceleration. We can take a look. It hit 60 amps. The power supply drooped down to like 40 volts. It's an unregulated supply with a transformer, rectifier, and a cap. The regen wasn't too bad here, but you know, there's no big mass attached to this, no large inertia, so that's pretty good. But you can trace the terminal voltage to see how bad your back EMF limit is, and I'm going to show it going too fast here. So we have to watch out for a voltage limit. So yeah, we're starting to get voltage limited here, and the following error builds up. So this motor requires a higher voltage. I think it's a 200 volt motor. You can get different windings, or you can get a Zenith. Thanks for watching.